Hello friends, so today we are going to discuss four questions, and these four questions are from electrostatics. One second. Okay, so we are going to discuss four questions from electrostatics, and in the first question, imagine a sphere of radius a filled with negative charge of uniform density, the total charge being equivalent to that of 2 electrons. Embedded in this jelly of negative charge are 2 protons, and assume that in spite of their presence, the negative charge distribution remains uniform. Where must the protons be located so that the force on each of them is 0? So basically, this is equilibrium of the forces, and question is asked in little bit, you can say not directly but indirectly. So we have a electric field, or we can say we have a uniform charge sphere, and that charge sphere is going to have a charge, and that charge will be dependent upon the this number of 2 electrons which are given to us. So we are going to start from there only. So first of all, we are going to find out the electric field of this negative charge uniform density, and then we are going to move toward the force part. So you can see our electric field, and we are given that we have a uniform charge sphere of radius a. Therefore, we can say total charge of the sphere, let us suppose that is our q, then this q will be equal to, because it is only 2 electrons, so that will be equal to minus 2 times E. And we already know the formula for a uniform electric field inside a uniform charge sphere. We can write that our field inside a uniform charge sphere at a distance r from the center. And let us call this electric field as E at a distance r. So we can write this as our electric field at a distance r will be equal to 1 upon 4 pi epsilon naught q times r and divided by a cube and our r unit vector. The q we already know, therefore we can write this will be equal to minus 1 upon 4 pi epsilon naught, q is equal to 2 times E, and we have this as our r divided by E cube This is our R unit vector. And we have to decide the geometry of the protons, how the protons will be placed. So we want that for the equilibrium configuration, if we have two charges, so we know the charges should be always in a straight line. So you can say that for equilibrium, configuration, the protons lie in a straight line. Straight line. And we assume that these protons are equidistant from the center, or we can say at a distance x from the center. So you can say each proton is at a distance x from the center. So we can just approximately draw the figure. So we have two protons. This is the first proton, this is the second proton, and this is the center. So this distance between these two protons will be equal to 2x, and with respect to center, the distance will be x. Now let's find out forces of one proton, because we have to test the equilibrium condition. So we can say forces on one proton So there will be you can say force because of the negative cloud, that is because of the electron, and the second force will be because of the proton and proton. So there will be two forces. So in part A, you can say force due to negative charge cloud. Force due to negative charge cloud. So straightforward, we can write its magnitude. So we can see F cloud will be equal to charge multiplied by the electric field, which gives us 1 upon 4 pi epsilon naught. This comes as 2e square, and at a distance x, and our a cube, and its direction will be towards the center. And the second force will be between the proton and proton. So you can say the second force due to other proton, and the distance between the two proton is 2x. So you can say the force between proton and proton will be equal to 1 upon 4 pi epsilon naught e square, and the distance between them is about 2x. This comes down 2x square, which comes as 1 upon 4 pi epsilon naught e square, and this is about 4x square, and its direction will be away from the center. So we have a center. Okay, so we can just draw it. Suppose this is a center, and the repulsion between the proton and proton is away from the center, and the force of attraction is towards the center. Okay, so you can say it is in this direction. So both are in opposite direction. Okay. Therefore, for equilibrium, the force due to cloud, or we can say electron and proton, should be equal to force between the proton and proton. So this is our force between proton and proton, and this is a force because of the cloud. Therefore we can say that for equilibrium, our force because of the cloud will be equal to force between the protons, and we know we have a common factor, that is 1 upon 4 pi epsilon naught, and 1 upon 4 pi epsilon naught common, so straightforward we can just ignore it, and we can write this as our 2e square a cube x will be equal to a square upon 4x square, and our e square cancels out. Therefore from here we get this as our 2x will be equal to our a cube upon 4x square. So this comes as our x cube will be equal to a cube by 8, or we can say our x is equal to a by 2. Okay, so this is the distance for the equilibrium condition. Okay, so this question was quite simple, only the statement of the question was a little bit tricky. Okay, they have assumed that it is a charge cloud portion, and this is also a little bit statement wise tricky. Otherwise, if you look towards the solution is quite simple for this particular question. So here we are given a figure shows a spherical shell of charge of radius a and surface density rho, from which a small circular piece of radius b, which is much smaller than a, has been removed. What is the direction and the magnitude of field at the midpoint of the aperture? So here the statement is little bit, you can say, tricky, but the solution is quite easy. Okay, it is as simple as that. Like we already have done this multiple times in case of the center of mass also, and in case of the charged bodies also. Okay, usually when we do with respect to the rotational motion, so here also we have a circular body, and from this, suppose it is circular, and from here we remove a small portion of this, so that this becomes a cavity. Okay, and same concept is there, but the question is asked a little bit tricky way. Okay, and so we are given that we are having a spherical shell, and the spherical shell is having a radius a, and its you can see charge density is given to us as a rho, and you can say that a small circular hole, because in this case we are given that this is our small piece, the radius of this is given as b, so it means this small hole is also going to have a radius of b, which will be much lesser than the radius of this sphere. Okay, so indirectly we are given that the radius of the hole is much smaller than a, and for that we can say that our small circular hole of radius, and that radius over b, which is much smaller than a, and the point of interest is the midpoint of the aperture. Okay, so we are interested in the midpoint of aperture here, or we can say this portion, midpoint of this aperture. And like I said, in this case if you want to solve this type of question, suppose we are having a uniform charge density rho is there, so this cavity is going to have a uniform density of minus rho, and in order to solve this type of question we always use superposition. Okay. So we use our superposition. So in the last video also we discussed this superposition with respect to 3 questions we dealt there. And so same principle we are going to use here. So you can say as per our superposition, and this superposition is going to give us an equation of the electric field, and which states that our actual electric field will be equal to electric field because of our full shell minus electric field because of the piece removed piece. So this is basically our superposition principle. We always apply this one in the shorter version, and we know that uniform charged spherical shell, the electric field inside that shell is always equal to 0. Therefore we can write that our spherical shell and we know that the field inside is equal to 0. Therefore we can write that our electric field of our full shell will be equal to 0. So we put 0 in this part, and this gives us that our actual electric field will be equal to minus of or negative of the electric field of our removed piece. Okay. So let's find out what will be the electric field that will be because of the removed piece. Okay. So we come to a field of a removed piece. And for case of a removed piece, we are given that B is very much less than A. Okay. Basically we have a sphere, and if you remove a small piece from the sphere, that will be partially as a sphere also. Okay. But the radius of the sphere, the removed piece, is very much smaller than A. Therefore we can say we can treat this removed portion as a uniformly charged disk. So as B is very much less than A, okay, therefore from here we can say the removed surface is locally a planar. Okay, so we can assume that it is some kind of planar surface, or from here we can write it that it can be treated as uniformly charged disk. You can treat it as a uniform charged disk. Uniform charge disk with surface charge density and that is our rho. Now we already know the standard formula for our electric field on the axis of a disk at a distance z. So we know that our field on the axis of a disk at a distance x, and let us suppose that is of E of z, then this will be equal to density upon 2 epsilon naught 1 minus z upon z square plus b square and its square root. Okay, so this is our formula for our field on the axis of a disk at a distance x. And we have to deal with the center of the curvature. Center of curvature means like a center of the disk. For that we can easily put z is equal to 0. Okay, so you can see at the center of the disk we have value of z is equal to 0. Therefore we can say that electric field because of the disk will be equal to sigma upon rho upon sigma upon 2 epsilon naught. And we already know that our electric field actual is equal to the negative of the electric field of the piece removed. Thus we can write that our electric field actual and the piece removed is in the shape of disk. So we can say this is equal to minus of electric field of our disk. And so we can, with respect to the direction, we can say that the field of the disk points away from the disk. We can say our direction, we can say points away from the disk, points away from the disk. And therefore we can write that the actual field is opposite, or we can say as disk is missing. And which we have already written here. So you can say the actual electric field will be equal to the negative of our electric field due to the disk. And if you are interested in the magnitude only, and we can say that the magnitude will be equal to over 2 upon epsilon naught. Okay. And here also we can just write the direction, and the direction will be toward the center of the sphere, normal. Okay, inward normal. You can say toward the center of sphere, or we can say inward normal. So this question was little bit tricky in the sense statement wise, otherwise the question we have done this multiple times, and usually we deal these type of questions like we have circular body and we create a cavity. So in this case we are interested in the cavity portion, the piece which we have removed, and usually we only deal with the object, but in this case we are interested in this cavity that is being removed. So for particular question, it is given, in this question it is given that it is a radius of B, and this B is very much less than our A, where A is the radius of the main body. So because of this, because the main body is given a sphere, so this body we can treat as a, you can say, for approximation we can treat it as a disk. So this is the only difference between the two, otherwise it is quite straightforward. Next question. Okay, so here we are given, consider three charge sheets A, B and C. The sheets are parallel, A above, B above C. On each sheet there is a surface charge of uniform density -4 on A, 7 on B and -3 on C. The density given includes charges on the both sides of the sheet. What is the magnitude of the electrical forces per unit area on each of the sheet, and the total force per unit area on the three sheets? Okay. So this we have also done, but we are mainly solve this question for our two sheets at most. Okay, and we deal with respect to electric field only. But here we are given that we are having three sheets. So we are having three sheets. So A is our topmost sheet, and then below that we are having sheet number B, and the lowest one is our sheet number C, and their charge densities are also given to us. A is having, suppose, our charge density of our sigma 1, sigma A, and it is given as -4 into 10 to the power -5. Then we have sheet B, let us suppose that is our row B, and that is +7 into 10 to the power -5. And then we have a sheet C, and it is also having a -3 into 10 to the power -5. And we have to find out the, we can say, the force per magnitude of electric force each of the sheet. Okay. And we have to remember that if you look closely, first of all, this is a -4 and this is -3. So -4 -3 is -7, and this is a 7. So it means the summation of all these charge densities is equal to 0. So this is A, B and C is equal to 0. That's from the question itself we can see. Okay, and we already know that when the charge density is greater than 0, or we can say positive, the field is away from the sheet. Okay. So we have a field which is away from sheet. And when we are having this charge density is less than 0, or which is negative, then we have toward the sheet. This is our toward the sheet. This is the standard notation. And for our infinite sheet, there is a, you can say, the value of electric field is only dependent upon the charge density. There is no mention about the distance. It is not basically dependent upon the distance between the sheet. So this is one of the easiest, we can, to solve it. Okay, no matter how much distance between the sheets are having between them, okay, the electric field will be always uniform. Okay. And we are supposed to find out force per unit area on a sheet. You can say that force per unit area on a sheet. So it means we are going to find a force oblique area. Okay. And we know that a particular sheet, it can be A, B or C, any of the sheet, okay, it is going to experience the force only due to the external field. You can say the sheet experiences force only due to external field. It means our F upon A will be equal to the charge density multiplied by the external field. So this is the basic formula which we are going to use. Okay. And this, in this particular case, our external field will be field due to other two sheets. Field due to other two sheets. So which basically means that if I want to find out the force per unit area on A, then the external field on this sheet A will be because of B and C. Okay. And if I want to find out external force on this B, then external field will be because of A and because of C. Okay. So in the three sheet system, we are going to find our external field that will be dependent upon other two sheets. Okay. This we have to remember. So let's find out what will be the external field at each sheet. External field at each sheet. And so we are having sheet A, then we are having sheet B, and we are having sheet C. And we know the charge density on A is negative, on B is positive, and C is negative. Okay. So other than this, we also, let us suppose we are dealing with sheet A. Okay. So first we are going to deal with our sheet A. So the field, or we can say the external field on sheet A will be because of field B and electric field due to C. And our B is having a charge density positive, so it's will be upward, and C is having a charge density negative, so its field will be downward. Okay, that's our standard. And therefore we can write that electric field because of B on A, and that will be equal to our the formula we already know is our charge density divided by 2 epsilon naught. This is the electric field because of our infinite sheet. So charge density in this case is plus 7 into 10 to the power minus 5 divided by 2 epsilon naught. Okay. And then we are having electric field, our C on A, and this will minus 3 into 10 to the power minus 5, and we have 2 epsilon naught. And now we come to direction from B to A, it will be upward direction, and from C to A it will be downward direction. Okay, because C is having a negative charge. Therefore net external, so we can say external field on A will be the subtraction because both are opposite. So this comes as our 7 minus 3 into 10 to the power minus 5 divided by 2 epsilon naught, which comes as a 4 into 10 to the power minus 5 and 2 epsilon naught. Now we come to sheet B. Once again, this is sheet A, this is sheet B, and this is sheet C. A is negative, B is positive, and C is negative. and we know the negative electric field is toward the sheet. Therefore, we can write that our electric field because of A on B. So this comes as a plus. 1 second. A is negative. Yeah. Okay. So this comes a plus, and this is 4 into 10 to the power minus 5 divided by 2 epsilon naught. Okay, and direction is our upward. Okay, I forgot to mention that we are going to take for upward, we are going to take as positive, and downward we are going to take as negative. And then we come to our electric field because of C on B, which comes as minus 3 into 10 to the power minus 5 upon 2 epsilon naught, and direction will be downward. Therefore, our external electric field on sheet B will be equal to 4 minus 3 into 10 to the power minus 5 and 2 epsilon naught, which comes as 1 into 10 to the power minus 5 upon 2 epsilon naught. And finally, we come to our sheet C. Sheet B, okay, and once again this is A, B and C. So this is negative, positive and negative, and we know for negative it is toward the sheet, and positive it is away from the sheet. Okay. So we come to our electric field because of A on C will be upward, so we are going to take that as positive. So this is plus 10 to the power minus 5 upon 2 epsilon naught, and direction will be upward. Similarly, electric field because of B on C will be equal to minus, and this is 7 into 10 to the power minus 5 into 2 epsilon naught. So we get our external field at C will be equal to 4 minus 7 into 10 to the power minus 5 upon 2 epsilon naught. 1 second. And this gives us minus 3 into 10 to the power minus 5 upon 2 epsilon naught. So we got the external field. Now we come to our force per unit area. Force per unit area. And our sheet A, which was our force on A per unit area, will be equal to charge density of A and external field on sheet A. This comes as our minus 4 into 10 to the power minus 5, and this will be our 2 epsilon naught and 4 into 10 to the power minus 5. So this comes as our, if we are interested in magnitude part only, F upon A will be equal to 8 into 10 to the power minus 10 upon epsilon naught. Now similarly, and direction will be okay, we will come to that later on. This is approximately equal to 90 Newton per meter square. Okay. This will be Next is our sheet B. In sheet B we have a force B per unit area will be equal to over 7 into 10 to the power minus 5 and 1 into 10 to the power minus 5 upon 2 epsilon naught, and this gives us that Fb upon A will be equal to, this will be our 3.5 into 10 to the power minus 10 upon epsilon naught, and approximately that will be equal to 40 Newton per meter square. Similarly, we come to sheet C. And sheet C, we have force C upon A will be equal to minus 3 into 10 to the power minus 5 and minus 3 into 10 to the power minus 5 upon epsilon naught. And so we get this as Fc upon A will be equal to, this will be over 4.5 into 10 to the power minus 10 epsilon naught, approximately equal to 40 Newton per meter square. So these are the forces per unit area. And so this was part A. We are supposed to find out the forces per unit area and the total force. So total force we are going to simply add them. So you can say total force, and in the starting we noticed that the summation of their charge densities is equal to 0. Okay. So from here also you can derive, or we can simply add them also. So Fa upon A plus Fb upon A plus Fc upon A, this will be equal to minus 16 plus 7 and plus 9 divided by epsilon naught into 10 to the power minus 10 is equal to 0. Okay, so total force per unit area will be equal to 0. Okay, next question. It states that a charge bubble experiences an outward electric force on every bit of its surface. Given that the total charge Q on the bubble of radius r, what is the magnitude of the resultant force tending to pull any hemispherical half of the bubble away from other half, should this force divided by 2 pi r exceed the surface tension of the soap film? So first of all we are going to find out the magnitude of the resultant force that is going to pull the hemispherical half. Okay, this is a little bit tricky here. The force is being asked on the hemispherical half of the bubble. Okay, so we will deal with that on the last part. Okay, but it is little bit tricky, so you can say here we can just use the concept of, if you are going to pull from both ends with the 10 Newton force, the total resultant will be a different result. Okay, it's not that much simpler. Okay. And so we are given that we are having a bubble of charge Q and radius r. So we are given a bubble which is having a charge. The charge is our Q and the radius is our r. Therefore from here we can find out the total surface area of the bubble total surface area of the bubble, let us suppose that is our A, which will be equal to 4 pi r square. Therefore, from here now we can find out the surface charge density. Surface charge density, that is our rho sigma is equal to q upon 4 pi r square. Okay, and this charge is, you can say, reside entirely on the surface. That is our, we already know this thing. Okay, so let me put it here. You can say this charge resides entirely on the surface. Resides entirely on the surface. And in case of our so we have to remember that the electric field on the you can say the electric field on the average, so we can say that the electric field acting on the surface is the average of the field outside and inside. Okay, so basically we are talking about the average electric field. Okay, so let me put it through. So we can say that average electric field and this is our E average will be equal to electric field at the external plus electric field at the internal and divided by 2. And we know that the field inside the bubble is, because it is some kind of spherical shell, so the field everywhere inside is always equal to 0. So you can say that our for a uniformly charged spherical shell, produces zero field inside, or we can say that the electric field inside will be equal to 0. Thus we can write that our external electric field, as per our Gauss's law, we can write that will be equal to sigma upon epsilon naught. That's our standard result. Okay. So you can say the field outside the bubble, and that is our E out will be equal to sigma upon epsilon naught. Thus we substitute both these in this particular equation, and we get that our average electric field will be equal to 1 by 2 sigma epsilon naught plus 0, which gives us sigma upon 2 epsilon naught. This is our average electric field that is associated with the soap bubble. And now let us find out that what will be the electrical pressure on the bubble surface, which is going to help us to find out the force. So you can say the electrical pressure on the bubble surface. And for that, let us consider suppose this is a bubble surface, and this is center, and we are going to consider a small area, so this is our small area of dA and having a charge of our dq. So consider a small surface element. Consider a small surface element, and that element we have considered dA. So from here we can find out the charge on this element, which is our dq will be equal to charge density multiplied by dA. And from here we can find out the force. So force will be equal to our dF, and that will be equal to our dq times average electric field. And we already know our value of our average electric field, therefore we can say that our force will be equal to our dq. We can substitute, we get this as our charge density multiplied by E average dA and n unit vector. Okay, that is representation of a direction. And electric field, we know that is always normal to the surface, so force will be following the same path. Okay, so you can say our n unit vector will be outward normal. So it means our n unit vector will be in this direction. And now we can find out the force per unit area, which is nothing but our electrical pressure. You can say our force per unit area, which is our electrical pressure. And let us call this as P. So you can say our P is equal to our dF upon dA. So this comes as our sigma upon average electric field. So we substitute value of our average electric field. So this comes as sigma multiplied by 2 epsilon naught, and this gives us square upon 2 epsilon naught, and we substitute value of our sigma in terms of charge. Therefore we can say that our P will be equal to 1 upon 2 epsilon naught, and charge density was our Q upon 4 pi r square and whole square, and this comes as our Q square upon 32 pi square epsilon naught and r raised to power 4. So this is our outward electrostatic pressure acting on the bubble. Okay. So this is our bubble, and this pressure will be acting all throughout the bubble, pushing it outwards. Okay, and that will be only balanced by the surface tension of that, which will come at the later part. You can say this is the outward electrostatic pressure. Outward electrostatic pressure acting on the bubble. Now, if you we also there is a term which is also called as a projection of the area. It is called as a projection of the, or we can say projected area. So if we know the formula for projected area, we can write it directly, which is equal to our pi r square. Okay, that is a projected area. If you do not know the formula, we can still drive it. It's not big problem. So let us drive it. So we are interested in a hemisphere. So let us draw a hemisphere. So this is our hemisphere, and this is our axis. And let us suppose, like, we consider a dA, small area, and that dA is at the angle of theta, and we are going to have a small force that will be acting in this direction. So we can divide that force into two components. So this will be angle theta, so this will be dF cos of theta, and this will be over dF sine of theta. And along with that, there will be asymmetrical angle also. Let us call this angle as phi, because it is going to rotate in this direction. We are going to move it. Corresponding to this, let us suppose this is our A, there will be opposite angle A prime. Okay. And here also we can divide this into two components. Okay. So from clearly we can see that our horizontal component will be balanced out. dF sine of theta, only the vertical component will be left. Okay. So this horizontal component will be balanced out. So for A, there is a prime, so it means for every right side will be having an equivalent point on the other side also. Therefore, we can say that we consider a theta as a polar angle with respect to positive z axis. Okay, so this is our positive z axis. So we consider a polar angle from positive z axis, and let this angle be equal to theta. Therefore, we can say for element dA, we already know the force is our dF, which is equal to our electrical pressure multiplied by dA. And like we said, that only horizontal component is going to survive, the vertical only vertical component is going to survive, the horizontal component will be cancelled. So we can say that horizontal component cancel, and only vertical component survives. Vertical component survive. Therefore, only the vertical component survive, that is in z axis. Thus, we can write that our dF z will be equal to our dF cos of theta, and dF we can put it, this is our PdA, and we have our cos of theta. And like I said, our phi is our azimuth angle and theta is our polar angle. So we have a phi is our azimuthal angle and our theta is our polar angle. Therefore, the total force separating the hemisphere let us suppose that is our F. So we can write our F will be equal to integration for our complete hemisphere and P cos of theta times dA. And our for sphere we know that our dA is equal to our r square sine of theta d theta as well as our d phi. And we can substitute it. So we get our force F will be equal to our PR square, and our 0 to 2 pi will be our limits of our phi, and 0 to pi by 2 will be the limit of our theta. And the integral is quite easy to solve. We get this internal one is going to give us 1 by 2 and this external one is going to give us 2 pi. Therefore, we can write that force F will be equal to PR square 2 pi times 1 by 2, which comes as a P pi r square. So like I said, this term pi r square is called as a projected area. So if you know the formula for this projected area, we can use force will be directly equal to our pressure multiplied by the projected area, which is our pi r square. And we can write that our force, we know that our P is equal to our Q square upon 32 pi square epsilon naught r4. Therefore, we can say that our force is equal to our Q square 32 pi square epsilon naught r4 multiplied by the projected area, that is our pi r square. Here square goes by pi and this goes by r square. So we are left with that a force F is equal to our Q square, and that is equal to our 32, and we have this as a pi, and one second, pi r square P r4, let me check. Yeah, Q square pi square epsilon naught r4, okay, it's correct, and 32 pi epsilon naught r square. So this is the value of the force. And we are given the question that this force, which is because of the electrical pressure, will be balanced by the surface tension. So we can say that suppose gamma is our surface tension, and which you can also write it as force per unit length. Force per unit length. And for hemispherical, we know that our length L will be equal to 2 pi r, okay, because the hemisphere is held by the along the equatorial rim. Therefore, we can write that our force upon 2 pi r, which is our tension, will be balanced by our q square and 32 pi one second, 32 pi epsilon naught and r square. And so if our this value of our f upon 2 pi r, if it is less than our value of a tension, so obviously our surface tension will be on the higher side, so bubble will be stable. Okay, so this will result in bubble is stable, because our, suppose this is the bubble and we have a pressure from the inside, which is our electrostatic pressure, and surface tension is going to balance it. Okay, so if the surface tension is having larger value, so bubble will be stable. But if the condition is reversed, so f upon 2 pi r is greater than gamma, that is surface tension, we are going to get unstable bubble. Unstable bubble. And this instability can results in the bursting of the bubble, or it can also leads to a deformation of the bubble. Okay, there are only two possibilities. And we can also find out what will be the critical charge for instability of the charged soap bubble. Okay, it is not asking the question, but still we can find out. Okay, so we are going to find out the critical charge. Critical charge for instability. And so we know that the one of the unique property that is associated with our you can say surface tension is that it tries to minimize the surface area. Because and the electric force, which is our electrostatic pressure, is trying to expand the bubble. So these are the two forces which are in opposite direction. Okay. So we already know that our force, which is trying to separate the hemisphere, we know that our force trying to separate hemisphere, and that is nothing but our, we already found out that is our electrostatic force. So we can say that is our F electrostatic, and that is our q square 32 pi epsilon naught r square. R square. And this is going to, you can say, pull the upper hemisphere upward and the lower hemisphere downward. So we can say from here that this force or we can say this is the total force. This is the total force tending to pull the upper hemisphere upward and the lower hemisphere downward. But so like we have drawn this, if we divide this into two parts also, upper as well lower, so this force F will be trying to pull the upper hemisphere in upward direction and the downward hemisphere in the downward direction. Okay, so this is the basic meaning here. And there is a restoring force which is of our surface tension. Therefore we can say that restoring force, and that is nothing but due to surface tension, and we can write that our F surface tension will be equal to our surface tension multiplied by 2 pi r, and this is the maximum force of the surface tension that is going to hold the bubble together. You can say this is the maximum force surface tension can provide to hold the bubble together. Therefore, for stability, electric force should be equal to the force due to surface tension, and we can simply substitute it. We have our Q square upon 32 pi epsilon naught r square is equal to our 2 pi r times gamma, and from here we can find out our value of charge, that is our Q. So where the Q will be equal to over 64 pi square and pi square epsilon naught gamma, and we have this as r cube. And in terms of our, we can just simplify a little bit. Therefore we can say that our critical charge will be equal to, this will be coming as our 8 pi and square root of epsilon naught gamma and r cube. And in general we can interpret from here that our critical charge is proportional to our r 3 by 2. It basically means that larger is the bubble, more charge it is going to hold, or we can say the higher surface tension stabilizes the bubble. So these were the 4 questions for today, and today we try to deal with 4 different type of questions specifically for our, we dealt with our 3 charge sheets, and try to find out what will be the external force on each of the sheet. Okay, suppose we were having 3 sheets, this was negative, these two were positive. So we try to sort it out, what will be the external force, and we have to remember that the external force will be equal to our charge density multiplied by the external electric field. Suppose we are going to find out the force on this A, so we are interested in what is the external field on this A, sheet A, and the external field on the sheet A will be because of sheet B and because of sheet C. Similarly, if we are interested in B, the external field on this B will be because of our A and because of our C. So this we have to keep in mind. And for this particular numerical, we found out that net total force on all the sheets, net total force on the sheet was equal to 0 because of the values which were given to us, and that also results in the stability condition. Okay. And in another question, it was basically a cavity question. So we are given that we have sphere, and from here we removed a small portion of it, little bit small portion, and a small portion is having a radius of B, and the sphere is having a radius of our A, and we are given that B is much smaller than A. So this the removed portion will be little bit of curved one, but because of this radius condition we can treat this as a disk, and then we can find out its electric field. Okay. And in this case we are interested in what is the value of the electric field that will be left because of this cavity, because we know in case of our spherical shell the net electric field inside the shell is equal to 0. Okay. But because of this small portion, which is a cavity portion, the electric field is going to, and we are going to use our superposition in order to solve it, because we have n number of times, many times we have used superposition, specifically in case of our center of mass or rotational motion. We take a body and we move from there, and then we use our principle of superposition. Similarly, in case of electric charges also, suppose this is having a charge density of rho positive, and this we are going to use U minus of rho. And in the last video we discussed that if we remove this minus cavity from here and fill it with another material which is having a different charge density of minus rho by 2. Okay. So that was another numerical in a different way, but the basic principle will be always because of the superposition. Okay. So we have to remember that whenever the cavity is there, we can use our principle of superposition. And this last question was our because of the soap bubble. And the soap bubble, first of all we found out, in case of soap bubble we are always interested in the average electric field, and the value of average electric field is electric field inside plus electric field outside, and inside is equal to 0, and so we are coming only this electric field formula is average electric field is electric field outside divided by 2. Okay, that's our basic this, and this gives us charge density and 2 epsilon, which is our standard formula for a bubble. Okay. And because of this it is a uniformly charged, so there will be electric pressure that will be created because of this charge, and this charge electric pressure will be balanced by the surface charge density, will be balanced by the surface tension. So we found out the force because of this electrostatic pressure, that is P times pi r square, and this pi r square is nothing but our projected area. Okay, we also derived this relationship for our projected area, and if we know the formula for projected area, then we can directly write it as pi r square. So we found out value of the electrostatic pressure, and we got the value of the force, and then we balanced out this force with our tension force, surface tension force. That is going to help us to find out what will be the value of the charge, and then we found out what will be the value of critical charge. So these were the few questions which we discussed today. So this completes all the 4 questions. Thank you.